Okay, so now we know something about acids, we know something about bases, we know how to calculate equilibrium constants for each, we know kind of something about the relationship of those equilibrium constants and how that relates to water, right? What we're going to do next is we're going to start to mix acids with their conjugate bases. So what happens if instead of starting with, let's say, the questions that I've given you so far have been things like, what if you have a 0.4 molar solution of acetic acid? What's the pH? And if you know the Ka of acetic acid, you can figure that out pretty easily, right? Use an ice table, all that other good stuff. What we're going to do this time is say, well, let's say that we don't have just acetic acid in our reaction. What if we have a mixture of acetic acid and its conjugate base? Can we figure out the pH? And does the pH change? What if we add more of one or the other, right? What if we start to manipulate this equilibrium? How do we keep track of what is happening in that solution based on the equilibrium constants that we know? Okay, so the first thing is to just kind of lay down some rules about this kind of thing. The first thing is that in general, conjugate bases of weak acids, right, produce OH minus, right? So if we have, let's say that we're starting with acetic acid. So acetic acid is here. Acetic acid has the molecular formula CH3CO2H, right? And we're going to react it with water, H2O, and we're going to make H3O plus the conjugate base. And that's going to mean that we transfer this hydrogen from acetic acid to the H2O, right? H2O has picked up a hydrogen to make H3O plus. That means that this one has lost a hydrogen. So now we got the conjugate base. This is acetate. It is the conjugate base. So once we know that that's the conjugate base, what happens if we add acetate? So we have this equilibrium that's all set up, and then we add acetate. So if we add acetate, what we're going to do is, of course, adding acetate changes Q. Right? Now remember that Q is, of course, the reaction quotient. This is from our previous unit, and Q is just if we tally up the concentrations at a particular point in time that is not equilibrium, right? So what's our equilibrium constant? Ka equals concentration of H3O plus times the concentration of the conjugate base, all divided by the concentration of the acid, right? So then when we add base, now we can look at Q. Q is concentration of H3O plus, conjugate base, plus the additional conjugate base, right? All over the concentration of the acid. So after we add more conjugate base, what is the relationship between Q and Ka, right? We're adding a higher concentration of conjugate base here. So that means our numerator is going to get larger. That means that Q is now greater than KEQ. And so we can go back and look at, well, what does that mean? If we make Q greater than KEQ, that means we're going to produce more reactants. Right? So to get back to equilibrium, what we have to do is, of course, make the denominator larger so that Q and KEQ become equal again. And so that means that we have to produce more acid. Right? So the way that we do this is the acetate makes OH minus, the OH minus reacts with H3O plus and becomes H2O. Right? So these two things react with each other. We make more H2O, and of course the consequence of that for acetate is that acetate becomes its conjugate acid, which is acetic acid. So this should not be surprising to you, right? Basically, this backs up Le Chatelier's principle. If you add products to your reaction, the conjugate base, you're going to push that reaction to create more reactants. If we added more acetic acid, we would create more products, right? Same thing, same deal. So when that happens, this is all well and good, but we just need to recognize that this is what's going to occur because we also want to be able to quantify this idea. So, pages here. Add more conjugate base, it moves the equations to the reactants. So this is interesting because what we've done is, of course, now we've increased the concentration of both of these things, right? So we've increased, well, I guess I should say, once we get back to equilibrium, upon reestablishing equilibrium, we will have greater concentrations of both acid and base. By adding more conjugate base, of course, we're not just increasing the concentration of the conjugate base because of Le Chatelier's principle and because of the way the reaction quotient relates to the equilibrium constant, right? I use KEQ here, but I could have used Ka, right? We're actually producing more acid as well. So when we have this situation where we have high concentrations, and high is definitely a relative term here, right? So the bigger the concentration is, the more this is true, right? High concentrations of both acid and base is a buffer solution. Right? So remember when I promised to make this stuff more complicated? This is that moment. Buffer solutions are much more complicated than just a straight solution of acid or a straight solution of base, right? So what are the things that we know about buffer solutions, or the things that we need to know about buffers, right? So instead of buffer solution, we often just call them buffers, right? The first thing is that it's a mixture of acid and base, which I kind of already said. Right? The important property of buffers is that they don't really change pH when acid or base is added. Right? And now this is kind of odd, right? We would think that normally, no matter what your solution is, if you add acid to it, it should become more acidic. That's kind of the definition of an acid, right? With buffer solutions, that's not exactly how it works. And if we kind of dig into the way that we calculate Ka and how that relates to pH is what we're going to do next. That's really going to hopefully clear up like how can we have the solution where the pH doesn't change when we add an acid or a base. That seems counterintuitive, but in fact, the algebra that we're going to do and the way that we use this because of logarithms and all this other stuff is going to kind of show us that in fact this is exactly how it should work if we understand the equilibriums and the way that the reaction quotient kind of forces these things to work, we're going to see that this actually ends up making sense. So the next video is all about the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is everything you need to know about buffers, right? So there's one equation, it sums up the relationship between the Ka, the Kb, and the pH, right? So all those things are going to be kind of put together. Depending on our concentrations of acids and bases, we're going to be able to figure out kind of we're going to be able to figure out how much a pH changes when we add acid and how strong of a buffer we have, right? So that's the next one.